Welcome back to meta-analysis. ESCI Intro Meta-analysis has 2 pages for Cohen's d, and I'm on the d subsets page. Why do we need to use d? If we have studies, for example these, that used a variety of different measures, we need to transform them to a single measure so that we can meta-analyze. And Cohen's d is a very common choice for an effect size for meta-analysis. In fact, one of the great advantages of d, one of the reasons for using d, is so we can meta-analyze. Here we have 8 studies, 6 of them from the Damisch group in Germany, all about good luck and superstition, and presenting consistent evidence that superstition and good luck can improve performance. These 2 studies by Bob Callan-Jagerman, my co-author, who with his students has done a number of important replication studies, that group did 2 careful pre-registered replications of the Damisch work, and here are their results. And they're much larger studies, and you can read in the book how they carefully swapped protocol videos with the other group to check that they were doing everything as closely as possible to the way that the original Damisch researchers had carried out their first studies. Now, when you use this page, you can enter in study names, D, your sample sizes for your 2 independent groups. Some of the other cells you can't click on or select because they're calculated. You enter your D, and ESCI calculates D unbiased. I need to explain about confidence intervals for Cohen's d. They're a bit tricky to calculate, and so you need to press this button at red 7 to trigger calculation by ESCI. You can read the pop-out here at red 7 all about it. So if I type in, let's say, 60 and 50 here, the confidence intervals on those Cohen's d values disappear and we need to recalculate. I'm going to click the button, and there ESCI took just a second or a moment to recalculate them all, and if I type back in the correct values, 66 and 57, we have to recalculate again, and there we are back where we started. So if ever you type in new data or load a new data set, be prepared when you're using D to trigger calculation by pressing the Calculate Confidence Intervals button. You can use these radio buttons to select which effect size to enter into your meta-analysis. So here we're plotting D unbiased values, and if I change this to D, all these points just move a little. Now they're a little larger because they're the biased value. Unbiased, there we go. Note that the interval estimates don't change. In every case, they're our best interval estimates of delta, the population effect size. Now, looking at these results, what strikes you immediately? Of course, that we have a bunch here and a bunch there. So do you think we have heterogeneity? Do you think that these studies may be estimating somewhat different population effects? Well, let's switch between the fixed effect analysis, a comparatively short diamond, and random effects, comparatively long. And in fact, the diamond ratio is 1.62. So that's really quite strong evidence that we have some heterogeneity here. But we can turn that to our advantage, because if there is heterogeneity, maybe we can identify a variable to account for some of it. Such a variable is called a moderator. And this is called moderator analysis when we seek a variable to explain some heterogeneity. Now here there's a clear difference between this group of studies and that one. They're done by different groups in different countries. And so let's label them. Let's choose a dichotomous moderator and study that. So our moderator is either Damisch or Callan. And here are the labels for those 2 groups. Now we click subset analysis, and ESCI does 3 meta-analyses. There's the original one of everything, just grayed out there. But what we're really interested in is the meta-analysis of just the red subset, and there's its result, and just the blue subset, and there's its result. And down here we have a difference axis, and it shows us that the difference between the blue and the red is round about 0.8 or minus 0.8 the way we calculate it. And that means overall these studies suggested a D unbiased of round about 0.8 and these studies round about 0. And here we can look at the confidence interval on the meta-analysis result over here for the two subgroups, 0.8 and 0.05. What do we conclude? That the dichotomous moderator of damage studies versus kaolin studies seems to be accounting for a fair degree of heterogeneity in the whole set of studies. And in fact, the diamond ratio for the red group and for the blue group is 1. If we click between fixed effect and random effects, you'll see no change in the blue and the red diamond. Fixed effect model is perfectly adequate for those. There's no heterogeneity within the red group or the blue group, but in the overall group, the grey analysis, there certainly is. Moderator analysis can be enormously valuable because, particularly if we've got a larger number of studies, we can get perhaps quite strong evidence that a particular moderator variable is doing some work for us, is explaining some heterogeneity. And we can even study a number of possible moderators and identify which one seems to be accounting for heterogeneity. That, of course, would be an exploratory analysis, and we need to follow up with targeted research. Note, however, that we don't have random allocation of studies to different conditions, so we can't make it causal conclusion. We're noticing an association, and so we have an interesting relationship that may be worth further study. And suppose that our dichotomous moderator was, say, males versus females. It may be that no single study has ever compared them directly, but in our meta-analysis we can ask a research question about what's the role of gender that no single study has ever looked at in this particular field. So that's another of the beauties of meta-analysis. It can even identify variables that may be of theoretical importance that haven't been considered before to be relevant. See the story in Chapter 9 about Peter Wilson's work on dyspraxia, clumsy children. Now I want to go back to the original two groups page where we're using original units and consider p-values. Have I mentioned p-values at all in relation to meta-analysis? No. And in fact, we don't need to. You can do all of meta-analysis absolutely happily and never consider or mention a p-value at all. If you want p-values, you can click here and turn them on. But those values will just confirm what you could eyeball by reading off where these confidence intervals fall in relation to our zero null hypothesis. Now consider selective publication. One of the ways that reliance on NHST and p-values has really damaged research in the past, because so many journals would only publish studies if they reach statistical significance. Now suppose in this collection of studies we removed studies that were not statistically significant. Let's start by removing a couple here that have effect sizes that are actually negative. So I'm going to unclick for that study, out it goes. As I'm doing this, note what's happening to this effect size down here, this overall result of the meta-analysis. Now I'll remove that one. And now I'll start at the top and I'll remove those confidence intervals that overlap with zero. So they'd be individually the studies not statistically significant. And there's another one. Out it goes. All this big one. The next one. And this next one. And I'm left with this result, an overall estimate of round about 0.3 as our estimate of the effect size in the population from the meta-analysis of the only two statistically significant studies. And so that will be a large overestimate of the effect that would be given to us if we had all the studies available to us. So you can see how if selective publication leads to a meta-analyst having available only the statistically significant studies, or more likely to have those available than the ones that did not reach significance, then we have distortion in the literature, and published results will be, on average, overestimates of true effects. Even the result of meta-analysis will give an overall estimate that's too large if studies that do not reach statistical significance are more likely to be missing. Selective publication based on p-value. It's called the file draw effect. Studies that were rejected by journals, or perhaps the researcher didn't even bother to write them up because they were not statistically significant. Weep. In Chapter 9, let's consider end of chapter exercise number 2. I'll go to the data file and I'll copy in the data to do that exercise. So first I'm going to clear here. There's no clear data button, but I simply delete everything there. Now I go to the data file, there it is, and I'm going to copy this whole slab of data, having checked carefully that it's set up to match how ESCI does it. So we have name, mean, standard deviation, n for one independent group, and then the same for the other. So copy, go back to ESCI there, and then paste values, paste special values, and there they are. So I've got study names, I've got mean, standard deviation, and n. I'll have to type in the appropriate labels up here for this exercise, and there I've got the meta-analysis, and this is a beautiful example of a large number, about 25 studies from various labs around the United States, studying flag priming, the extent to which exposure to the American flag might lead people to express more conservative political attitudes. And it looks as though the answer from all these replications is there is no effect, or an absolutely trivially tiny effect. Just to summarise about meta-analysis, well, first, it gives us more precise estimates, as here. Second, it allows us to identify moderators, and this can be immensely important and make a big theoretical contribution. And it allows us to integrate evidence over studies and provide the best possible evidence based on current research for practitioners. So it gives the basis for evidence-based practice. I hope you enjoy reading in Chapter 9 about the Cochrane collaboration, one of humanity's great achievements, and various other stories of how meta-analysis has made a real difference. Cochrane, yes, they don't call them diamonds for nothing. A treasure trove of integration of research results, just what we need for evidence-based practice. Meta-analysis, of course, is intimately integrated into open science. Open science urges replication, which means meta-analysis to integrate those results, and so the two go together totally. Enjoy. The steady march upwards from confidence intervals to the results of a meta-analysis. A shiny diamond.